Moving ahead, section 10-6 to torque. This is skipping ahead in the material, but it's material that's more relevant for the lab, so I want to move it up in terms of when you saw it. So torque. The analogy I always like to think of with torque is that of a door, right? So if you imagine a classic door like this, especially a big, heavy door, if you want to go to open the door, how do you push on the door? How do you exert a force? Well, if we were in class, I would demonstrate this, right? If you try and push near the handle, the door opens fairly easily. But if you instead push somewhere on the other side than the handle, near the hinge, you have to put a huge amount of force into opening the door. And that's just where you apply the force. What also matters is what direction you apply the force, right? You'll get a different effect on the door if you apply it into the handle versus if you try applying a force from, say, this outer edge of the handle and push in towards the hinge of the door. That's not going to have a huge effect. So I encourage you to try this. Even if you don't have a heavy door, try pushing it at different places and seeing the difference in the effect. This illustrates the idea of torque, where torque, in its short, is the force necessary to rotate an object. The key being, so torque is our rotational equivalent of force, but it's looking at how it can cause a rotation, a force that can cause a rotation. And as we discussed with the door, it depends on both the angle of force, how you're applying it, and where you apply that force. So we could resolve our force into components to see how it affects rotation. So here's an example with another, we'll call it another egg. There's this nice teal egg here that has a rotation axis that's fixed in place over here. If we apply a force that's kind of at a glancing angle, then only part of that force will actually go into causing the egg to rotate, right? If we break the force into a radial component and a tangential component, we would see that the radial component is just pushing the egg against that rotation axis. It's not actually causing the rotation. What causes the rotation is the tangential component that's perpendicular to the radius, where the radius is drawn from the rotation axis to where the force is being applied. So that's what we want to think about. The other way you could look at this, and we'll see more of this down the road, is you could think of the full force, but then the effective moment arm or lever arm, which is the R perpendicular here. I'll stop moving the mouse for a moment so that we can see what's below. Because if you know the moment arm distance, then you can use the full force. It gives you sort of the effective radius that that force is acting at. It's another way of looking at it. So torque takes all of these factors into account. Torque, we use the symbol tau. It's a Greek letter. And it's equal to the radial distance from the axis of rotation to where the force is being applied, times the magnitude of the force, times sine of phi, where phi here is the angle between the radius and the force, which you can see on the previous slide if you want to double check that. So it's not just any angle, it's between R and F. And so we say that if you extend a line through the applied force, that's our line of action. That tells you where the force is acting. It's somewhere along that line, either forward or backward from that direction. And then that moment arm that we mentioned on the previous slide is the perpendicular distance from the line of action to the axis of rotation. So where you can get that perpendicular intersection. So encourage you to check that out in the figure on the back slide and ask questions as you have it on that. Now, if we get to the unit of torque, we can figure it out based upon the components that we have here, right? Sine of phi isn't going to have any units, so that's easy. Units of force are newtons, and the units of radius, or of a distance, are meters. So the unit of torque then is just going to be the newtons times the meter, or the Newton meter. Now, an important note here is that newtons times meters is in fact equivalent to that of my favorite unit, the joule. But we don't express torques in units of joules, great as the unit is, because torque is not energy. This is an interesting case where the units happen to be the same, but the quantities are very different. So we express torques as Newton meters and energy or work quantities as joules, to keep those two totally separate. Okay, and just as we saw with our rotational variables, we define torque to be positive if it would cause a counterclockwise rotation, and otherwise we say that it is in fact negative. So you could imagine this where if I have a bar here, if a force acting on the bar would cause it to rotate, if that's the only thing acting on it, to rotate clockwise, then we say that that is negative torque, right? But if instead I have a force that could cause a counterclockwise rotation, that is a positive torque. And if we have several torques, the net torque or resultant torque is just the sum of all the individual torques, much like what we did with our forces. When we found the net force, it was just the sum of all the individual forces added together. Okay, so let's look at a checkpoint with torque. Checkpoint 6, the figure shows an overhead view of a meter stick that can pivot about the dot on the position marked 20 for 20 centimeters. All 5 forces on the stick are horizontal and have the same magnitude. Rank the forces according to the magnitude of the torque they produce greatest first. So I want you to think about this and choose an answer. I want you to decide on an answer and write it down before you move on. So go ahead and hit pause right now. Okay, hoping you did that. We can double check. And the answer is B. So if you mark that, congratulations. Let's take a look at why. Well, it says that the greatest torque is from force 1 and force 3, versus the least amount is from 2 and 5. Why 2 and 5? Well, 2, notice, is right on the axis of rotation. So R is 0. So the torque from 2 is 0. For 5, it's not right on the axis of rotation. It's at 80 centimeters away, but the angle that it's being applied at is 0 degrees from the radius. So sine of 0 also gives you a torque of 0. So those two we can rule out as being the least amount of torque, and then we just have to compare 1, 3, and 4. And 1 and 3, because they're perpendicular to the radius, will have the largest amount of torque. 4 is at the same distance as 3, but because it is at an angle that is less than 90, between 0 and 90, it's at a value of torque that's intermediate or in between. And note, it's here focusing on the magnitude of the torque, so it doesn't matter if it's a positive or a negative torque. So that's why 1 and 3 are in fact the same. Okay, let's keep rolling into Newton's second law for rotation, which is just an expansion of our idea of torque. Since we know torque is like force, we expected to see Newton's second law appearing yet again. And so we're rewriting Newton's second law, F net equals ma, with rotational variables. So torque net instead of F net is equal to I, the rotational inertia, times alpha, the angular acceleration, where angular accelerations are equivalent of linear acceleration, and rotational inertia, as we briefly saw in lab and we'll get to see later on in chapter 10, is the rotational equivalent of mass. What is this saying? In short, it says that if you have a net torque acting on an object, then there's going to be an angular acceleration. It can't be staying still, right? It's going to have to be changing its angular velocity and either speeding up or slowing down. And that's what's shown here, where we have a mass on the end of a rod, where the rod has a fixed axis of rotation. And when you apply a force to it, the torque that comes from the tangential component of the force will cause this angular acceleration around the axis so that the mass is able to speed up and move faster and faster. All right, so taking this into account, we have another checkpoint, checkpoint 7. The figure shows an overhead view of a meter stick that can pivot about the point indicated, which is to the left of the stick's midpoint. 2 horizontal forces, F1 and F2, are applied to the stick. Only F1 is shown. Force 2 is perpendicular to the stick and is applied at the right end. If the stick is not to turn, A, what should be the direction of F2? B, should the magnitude of F2 be greater than, less than, or equal to F1? So I do want you to think about this, and again, write down your answer. So please take some time to do that. Go ahead and hit pause right now. Okay. Well, now we can double check the answer, trusting you did that. So find that it is D, that F2 should point downward, as well as that it should have a smaller magnitude than F1. Now, why is this? Well, if we draw in the force, we know it's at this right end of the stick. And so we could imagine, if we can think of something balancing here, if the pivot's fixed, if we have one force that's pulling down already, then the only way we can balance it out is if on the other side, there's a force that's going down. So that will be our F2 there to balance out F1. And you can try this out. This actually works really well with torque problems, is you can use your fingers as the pivot point. I'll just switch to one actually. You can use your finger as the pivot point to hold it in place, and then you can try pushing from either side, right? And if I try pushing one up and one down, then it doesn't work. It's even easier actually if you do it on a table, because then you have a little bit of support, but I can't show you as well on the table. Now, what about the magnitude? Well, the key is that the stick is not to turn. For the stick to not turn, that means that our angular acceleration must be equal to 0. And based on Newton's second law for rotation, the net torque also needs to be equal to 0. Well, we have a torque from force 1 and from force 2. They're in opposite directions. So if we sum the torques, 1, torque 2, those need to come out to 0. And let's check the sign of the torque, because we can about this pivot point. If there's just force 1 acting on the meter stick, then it would pull the meter stick in this counterclockwise direction. So I'm going to call that positive, versus force 2 is pulling the meter stick in a clockwise direction. And so that is a negative torque, because clocks are negative. So this tells us that the torques need to be equal and opposite in magnitude, right? That in terms, opposite in direction, equal in magnitude. So torque 1 in magnitude is equal to torque 2. And we know that the torque can be calculated with our RF sine theta. And since the forces are being applied perpendicularly to the stick, we'd be able to plug in a sine of 90 there for our angle, which technically is phi. So if we note that the torques have to be the same, then we have to compare the R's and the F's. And the R is already set by the problem. So for F1, the R is around 20 probably. But for F2, it's about an R of 80. We don't know the exact numbers, those are guesses. But what does that mean? That means the R for F2 is much, much bigger. So if the R here, R2, gets so much bigger than R1, then for the force on 2, it needs to be much, much less in order for the torques to still balance out. All right, so this gives you an idea of how you can set up these torque problems, especially involving Newton's second law for rotation. And we'll get to try this out in lab this week. So that's something to look forward to. See you soon.